Hyvää iltapäivää. I'm a little bit late, but I will start now. I opened the PDF file which you may find from the Moodle, which is a part 1 of the matrix calculus, and I will go some concepts through with this PDF file, but I will take some examples by using paper and pen and paper, and also Excel. So some examples how to use Excel in matrix calculus. You may read this PDF file when you have more time, probably more exactly. But this matrix algebra is quite powerful method to solve many problems concerning, for example, technical calculations. There are some examples there. In this course we will go through some basic calculation rules of matrix algebra, but as there is, you can see from the PDF file, of course this matrix algebra is not efficient way if you have to solve problems with matrices and using only pen and paper. Then that is not very effective. But if you have some calculation software, for example Excel or MATLAB or MATCAD and some other also, then it will be helpful, this matrix calculations. First, this definition here, if I can show that to you. Actually this matrices, these are actually some kind of spreadsheets, or you may think that they are some kind of tables of numbers, concerning numbers or numerical values. Those can be every time you may think, if you have some kind of rectangular table where there are some number of rows and some number of columns, then you may always think that is some kind of matrix. And from the picture you can see two probably most popular way to notate matrices. You may use those rounded parentheses or brackets in that first picture there. Here. This is probably the method I mostly use in my examples, but not in everywhere. I probably have that kind of habit. I'm not sure if I check that is my PDF, is that so, but many times when I calculate with matrices with pen and paper, I many times use those rounded parentheses there. But in written text, when I use computer and write there some examples concerning matrices, I many times use those so-called square brackets, those which are in the right hand side of the picture. But there are also other ways to notate or mark those matrices, those curly brackets. In Finnish we say aaltosulku, wave brackets in Finnish. I'm not sure if that is an English version also. And the last one is that angle brackets. You may find every all those kind of notations in matrix calculations, but I think in Finland at least mostly those two first versions are used, so those which you can see from the picture. Those names of the tables, these numbers inside of matrices, we can call them elements or entries. In Finnish mostly we use the word alkio it is exactly the same as element. Well, not exactly. The element word, if you think of chemistry, these elements, carbon and oxygen and hydrogen, and what those elements are, in Finnish we call them alkuaineet, elements. But in this meaning, element, mostly we use this alkio word. But in English, almost you may call them entries of the matrix, or those are those numbers inside of the matrix. And the method how we notate these elements is this kind of method. Mostly we name these matrices by using those uppercase letters or capital letters. For example, big A and big B and big C, etc. And then these elements, we mostly use the same letter there. If the matrix, the name of the matrix is A, uppercase A, then the elements are named with the same letter, but many times with the lowercase letter or small letters. But there are exceptions. For example, I can show that I have here formula book, Finnish formula book, tekniikan kaavasta, and here you can see that here they have used the same uppercase letter inside of those matrices, big A there. But it is not so important. You may choose what you like. But then the logic in these numbers, which are in subscripts here, A11, probably I told somewhere there that you can't read here. We don't say that this is A11 and A12 or A21. This is not a number which is higher than 10, but these numbers tells us the place in the table where that number is located. For example, this first number or first element there, it is located in first row, this horizontal row, and first vertical column. So both are first. So it is in the first line. I can paint that probably. Yeah, no. It is in first line and first column. And for example, this A21 or sorry, A21, it is located in second row and first column. So that is the logic in those subscripts there. And then the dimension or type of matrix, in that concept we mean the number of rows and number of columns in that matrix. For example, here the matrix A, it is called so-called matrix of type 2 by 3, or you may also say that the dimension of that matrix is 2 by 3. So this means that always the first number tells the number of rows, number of those horizontal lines there, or horizontal rows. So in this case it is 2. There are 2 rows in this matrix, and the last or the second number tells us that there are 3 columns in matrix. As you see, three vertical columns there are. In Finnish, I don't know if this is told there, but well, you can see it from my table formula book. In Finnish we call rivi is the row, and sarake is the column in English, in Finnish. So this is an example of matrix of type 2 by 3. This dimension or the type of those matrices are quite important because these matrix calculation rules many times they depend on what are the types of matrices. For example, you can't add two matrices if they are of different type. It is quite natural when you understand or see what is the calculation rule of sum of matrices, then it must be so that they have to be the same time, or that means that they have to have same number of rows and same number of columns to be able to add two matrices. And here this notation, I've written there the names of elements. For example, if I pick here element A21, you find from second row and first column, so it is this number here, and as you see, it's the value of the element A21 is 5. And there are another example there also, matrix of type 3 by 2. In Finnish we would say matriisi on tyyppiä 3 kertaa 2. This multiplication mark there, that we can say that kertaa 3 kertaa 2, 3 times 2 actually, if you translate that in English. So in this case there are same numbers here, 2 by 3 and here 3 by 2, but they are different kind of matrices. As you see, I have used here those square brackets in the first example, and the second example those rounded parentheses or rounded brackets there, but it doesn't, it is, you may choose which way you like to notate the matrix. As I probably told, or I meant to say that these rounded are many times easier to use when you are calculating by hand and you use paper and pen and paper. It is more, you may write that rounded parenthesis or rounded bracket more quickly than, for example, these square brackets. And then this some other concepts, square matrix, because the matrix is always a rectangular table of numbers, so it is probably quite easy to understand that the matrix is square matrix if the number of rows and number of columns are equal. So there are exactly the same number of rows as there are columns. So these square matrices, they can be, oh sorry, you can't see the whole text. Square matrices 2 by 2, 3 by 3, 4 by 3, 4, etc. And as there is some how do you say? It is also possible to speak about square matrix 1 by 1. So matrix which has only one row and one column. So if you just think that there has to be only one number inside of that kind of matrix. Of course, this type always tells how many numbers there are. For example, 2 by 2 or 2 times 2 tells us that there has to be 4 numbers inside of that kind of matrix. So this 1 by 1 or 1 times 1 gives us only 1 element inside of matrix. And we can say that this kind of matrix is actually a real number. It is only a number which is written inside of matrix or in some for some reason. But probably this is quite an exception. I don't know. So many application for matrices which are 1 by 1 matrices, but of course in theory it is possible to speak also that kind of matrices. So those names of matrices, they can be whatever. I mostly use these first letters A, B, C, but that is a matter of choice. You may choose whatever name you like to have for a matrix. So these names has nothing to do with those matrices. Well, there is one exception. The letter I, uppercase I, is a special one, and we will see a little bit later why that is a special case. But here you can see one kind of matrix, square matrix, 2 by 2. Then more concepts. Diagonal. When you have a square, well, also in rectangle, you may draw a line from corner to the corner or in the opposite side of that rectangle, and that is called diagonal. You may call that diagonal. And in square matrix it is defined so that those diagonal elements in square matrix are always those elements which has which locate in the first row and first column, or second row and second column, or third row and third column. So that means that, for example, in this square matrix, these which I have collected together, they are all in diagonal. So these elements are diagonal elements. There are in some matrix calculation rules. These diagonal elements has something special use, but I'm not sure if we will go through that during this course. I'm not sure, but you may find some kind of calculation rules where you use only those diagonal elements there. But it is important to know that, or understand what is the main diagonal. The ones with which row number and column number are equal. Yes, and the concept diagonal matrix, those kind of matrices in which there are, I would say that that kind of matrix which has almost zeros, only zeros inside of it, but only non-zero, or only elements that are not zero are located in the main diagonal. And if that is the case, then the matrix is called diagonal matrix. For example, this kind of matrix here, there are zeros or in all other places than in the main diagonal 1, 8, 4. Actually, that does not say that if you read this carefully, whose only non-zero elements are on the main diagonal. This, if we are careful, read that carefully, that does not say that you don't have any zeros in the main diagonal, but that means that in every other place than in main diagonal you have to have zeros. As you see, if I take away these elements, then I have only zeros left. And the diagonal matrix, it has some special properties, and that's why this kind of matrix has got a special name, diagonal matrix. One special case of that kind of matrix is so-called unit matrix. In Finnish we say yksikkömatriisi. I will check if I find that. Yeah, that word from my formula book. Here you can see this first one here is in Finnish neliömatriisi. Neliö is same as square. So this is square matrix, as you can see, because those indices of the elements here, the last element in the last row and last column, it has the indices nn. So this means that this is in the nth row and nth column. So that means that there has to be same number of rows and columns. And this is what in Finnish that exactly that has been said in this line. Neliömatriisissa on sama määrä rivejä ja sarakkeita. Rivi is row and sarake is column. Sama määrä, same number rows and columns. And this was the square matrix. And this matrix here is also a Finnish word, lävistäjämatriisi. That was the diagonal matrix. So as you see here, there are zeros here and zeros here, but all non-zero elements are located in the main diagonal. So this is called diagonal matrix or lävistäjämatriisi in Finnish. Lävistäjä is this, if you draw a rectangle and draw a line from this corner to this corner, and this line segment there, that is called lävistäjä in Finnish. And here is the yksikkömatriisi, which is same as unit matrix. Yksikkö is the same as unit in Finnish. You may think that this means yksi is the number one in Finnish, and yksikkö means that or you may think that means that it has something to do with the number one, this kind of matrix. But also yksikkö can, with the longer word yksikkö, is the same as unit or dimension. For example, 5 meters. This meter is unit, and in Finnish yksikkö. Meters and Celsius and square meter and volt. These all are yksikkö in physics. So here this letter, this uppercase I or capital I is a diagonal matrix in which the elements in the main diagonal are all one, exactly one. I have to say that in this book it is told that also E, uppercase E or capital E is also a name for a unit matrix, but I have to say that I don't so often actually I don't think, probably I have never seen a E letter for the unit matrix. This I is more popular way to name that matrix. And then I will go again here. Sorry. So as I told probably that this unit matrix that has something to do with number 1. You may think that because there is another way to name this kind of matrix, identity matrix. In this my formula book there was only one name for that in Finnish, but in English identity matrix or unit matrix that means the same. But you may think that the uppercase I in the name of the unit matrix or identity matrix comes from the word identity or identity. How do you pronounce that in English? Identiteetti in Finnish, identiteetti, matriisi, yksikkömatriisi. You may think that the uppercase I comes from the word identity, but you may also think that it comes from Roman numbers, Roman way to notate numbers, and this kind of letter was a number 1. If you needed number 2, then you used two I's, two uppercase I's there. And also that is a good way to think that, because if you think that this is some kind of number 1, that is actually this has lots to do with the number 1. Because, for example, if you think real numbers, these numbers in which we calculate in real world. For example, if we have a number 7 and then we multiply that with the number 1, 7 times 1, we get the result 7. So that means that this multiplying with the number 1 did not change anything. 7 times 1 is still 7. And also if you change the order, 1 times 7 is again 7. So you may say that this 1 is some kind of neutral element in a multiplication. That means that if you multiply with number 1, then that does not change anything. And in a matrix calculation, this unit matrix or identity matrix has the same property. If you multiply with this I, then you have a matrix, for example matrix A, and if you multiply that with that identity matrix, then that matrix A does not change at all. If that multiplication is possible to do, we can see that not every time the multiplication in matrix calculation is allowed. It is not as in real numbers. In real algebra, in real numbers, we can choose whatever number we like, 17 and 1,015,000, and if we multiply them, we can that always do. It is always possible to do that. But in matrices, if we have one matrix here and another matrix there, and we try to multiply them, most probably we can't do that, because there are some demands which we need to have that if we want to multiply two matrices with each other. So here for example, this is probably the most I would say that these two unit matrices are probably the most usual identity matrices or unit matrices. This so-called I2, that means that it is an identity matrix or unit matrix which has 2 rows and 2 columns, and the elements in main diagonal are ones and other elements are zeros. And also this 3 by 3 identity matrix, all elements in main diagonal are ones and other elements are zeros. So in that PDF there has been something, I don't know if that is there. Yes, you may think that is there any use, or why do we need those kind of matrices? If you multiply with unit matrix, nothing changes. Of course, you may also think that why do we need a number 1 in basic algebra? Of course we need that, because we can't do anything if we don't have that unit, that number 1 in basic mathematics, because that is some kind of starting point. If you have 0 here and you have 0 number 1 there, then you know, for example, in coordinate axis, you have this origin and you point, find out where is the, for example, x coordinate 1, and if you find the place for x coordinate 1, then you may find the places for x coordinate 2 and 3, etc. So if you don't have that number 1, you can't do anything actually. But probably the most important thing concerning this unit matrix is that gives us the possibility to do, for example, solve equation in matrix calculation. So we in the same manner, when we have equations of real number algebra, the usual algebra, we can solve those equations, and that solving of equation is actually impossible if we don't have the number 1. And in the matrix algebra the same holds. We need to have a so-called unit matrix to find out the solution for matrix equations. And then there is also zero matrix. This has the same use as a zero in normal algebra. We need zero. That means something that does not exist, and we may think that the zero matrix this has something similar to do in a matrix algebra than number 0 in normal algebra. Probably if nobody never thought what kind of matrix is zero matrix, probably most of us would have guessed what would that be. This is also something which has to do with matrix equations. If you compare to basic algebra and solving equations, we always have this equal sign in equation. That equal signs makes an equation. You need that equal sign there. And if you move everything from the, for example, from the right hand side of that equal sign there, then everything has moved away, so there has to be something, and that something is zero. And the same holds in matrix algebra, that when we are solving those sort of matrix equations, we need a concept of zero in matrices. So that is a zero matrix. But then these rules for calculating matrices, most of them are quite easy, and actually all calculation rules are very simple, but the multiplication rule is a little bit strange. Probably I don't know if I would have invented the matrix calculation, probably I would have not I would not have chosen that kind of rule for matrix multiplication, but that is only because I am not clever enough as was those guys who invented this matrix algebra. There is a reason for that the rules for matrix multiplication are that kind of strange rule. But the sum of matrices is very simple. Probably I already told that in the beginning. If you have two matrices, let's take this example here. If I have matrix A and matrix B and elements are like that, first thing you have to be sure that these both matrices are of same type, or the dimension of those matrices. Actually there is X here, I have chosen a wrong letter. It should be this multiplication mark there, but now I notice that I have used only a letter X here, but maybe not a big mistake. So these both matrices have to be the same type. They have to have the same number of rows. As we see, both have 2 rows, and they have to have same number of columns, and they both have 3 columns. So it is possible to do this matrix addition, and it is very simple rule. You just add those elements which are located in the corresponding place. For example, 2 plus 5, that is the sum of the element of the sum matrix, and the same holds there in the other elements there. Very simple rule. If we use Excel and add the two matrices, or calculate the sum of matrices, it is very easy way to do that. I will do it here. This is the first matrix. If I calculate with Excel this matrix calculation, I many times do so that I enter the entries or elements of the matrix there, and then mostly I get this kind of border there, so I can see that here is some kind of matrix here. And the second one, 5, 1, 4, minus 2, minus 2, was it 3 and 6, and I want to add these matrices. So it is very simple. I check that I have the same matrices there. Yes. So in the Excel you just write a formula here. You pick this entry here and plus this entry. So A1 plus E1 gives us the first element. 7, of course it is 7, because those two numbers have to add together. And then I just copy this formula. So first element there, and I copy that there and here like that, and this will be I will use a yellow color to show that. In my Excel sheets many times this is only my habit or way to do. So I many times color with yellow those elements in Excel sheets which has a formula in it. So for example, these are simple numbers, I just wrote them there or typed them there, but in here we have formulas. This is probably a good habit, because when you see a Excel sheet, even though if you have done that by yourself, if you haven't used that for a long time, you probably don't remember how does that Excel sheet work. So if you have some kind of color code, you probably can understand that here is something which has been calculated with these elements here. So this is easy to do with Excel. As here you saw that for example, this kind of problem, if you do that by hand, you have a of course these numbers inside of matrices in my examples are very simple one. Those can be whatever numbers, they can be decimal numbers, and if you have decimal numbers inside of those matrices, then you can understand that this is very slow method to calculate by hand. But in Excel you just have to type the numbers there, and then this formula holds it. You don't need to change this at all. For example, if this value changes, you just change this value and then the formula holds still. You don't need to change anything. And if you like to copy this, for example, you have to do this with other elements or at other matrices. You may only change these values here, and you can see that in the yellow part the numbers are changing there. Let's change that also, like that. Always in Excel, it doesn't matter what you are doing. The first time you make a formula there, it takes a time, and it is a slow step. But after you have made that Excel sheet, then you can use that, and then every time you use the same many times the same Excel sheet, then it is all the time more helpful for you. It helps you to go through some basic simple calculations, but which would take a little bit more time by doing that by hand or calculator. By the way, in some calculators there are also possible to calculate with matrices. I will show this. I don't like. Sorry, you don't see my calculator. Actually, I don't like the calculator when using that for matrix algebra, because if I compare this, for example, to Excel, this is some kind of old-fashioned equipment, I would say. But in this calculator, and also in some other graphic calculators, actually I don't have right now with me any other calculators which would which have the possibility to use matrices. But here you can see those square brackets. Here I will show this with my calculator, because some mathematical programs use the same method as this calculator does. There you can see those square brackets. I will try to find the same example to be able to get the same result. I will use the square brackets. I will take first those square brackets, and then I have numbers there. the first matrix was the first row was 2 3 4, so I will add 2 comma 3 comma 4, and then I try to find well, I will do this more universal way, which is the most common way to do this by calculators. Square brackets, and then I will write another square bracket there, and inside of that square bracket I will write the first row 2 comma 3 comma 4. So there is the first row of that example. Then I will go there outside of that square bracket, and I will take another, so that will give me another possibility to write the second row 5 6 7. That was the so now I have typed there the first matrix. I will show that from Excel. Those in the upper left corner there, it is the same matrix, and then I have in this calculator. If I now press enter, you can see that it's changed that to matrix, even though I didn't write it like that, but it understood that that was a matrix. And then I will do the same with another matrix there. It was 5 1 4 5 comma 1 comma 4, sorry, 5. This was the first row, and then the second row also inside the square brackets, and it was minus 2 comma 3 comma 6. So this is the second matrix, and again when I press enter, it gives me the matrix there. And then when I want to add those matrices, I just pick the first one here, and then plus, and then pick the second, oh sorry, here, second one. So there is I hate this document camera like this. Probably you see the plus sign in between those matrices, and press enter. That gives us the same result than we got from Excel, and the example there 7 4 8 and 3 9 13. So this gives us the same answer. Then probably I will have a break now, because I have to save this recording, because this is stupid, this ScreenPal program. It sometimes when you got too long recording, then you may get some problems with your computer, so I have to save this in this time. Let's continue at 15:25.